Thank you, Fernando, for the nice introduction. I will continue with the presentation. As said, would be on pumps and circulators and Ecodesign and so forth today. The agenda, I think, will start on the water pumps today. Talk a little bit about the Ecodesign regulation, what's been regulated so far, and how we actually do the compliance testing, at least in my part of the world, in Denmark, where we have done in my company quite a lot compliance testing on both motors and pumps and fans and so forth, and I will demonstrate how to actually perform it. This goes both for water pumps but also on the circulators, which is two very different things, of course. And finally, I will try to illustrate an example on the motor systems tool in a live sharing my desktop session, which we will hopefully succeed in this day as well. Yeah, this is just me. I don't think we need that. So let's get on the water pumps. First of all, the regulation on water pumps was decided and published in the European Union Official Journal in the summer of 2012. It was called 547-2 2012, and it was based on the findings of the preparatory study of Lot 11, which was done earlier, years before, by a different group. The first tier of the regulation started on January 1st, 2013, and the second tier in 2015 this year and January 1st. So both tiers are actually active at this point in time. From the preparatory study, we expect something like 3.3 terawatt-hour savings in 2020 due to these measures if we compare it to no measures at all. And another thing that's important to realize is that this regulation is focusing on the component, the pump as a component. Efficiency of the pump itself, in this case 3 duty points, and we do not take neither duty cycle or load profile into account in this regulation on water pumps. So that's good to know. The scope of the regulation is basically rotodynamic water pumps for pumping of clean water, also pumps integrated into other products. So that's quite a large scope, you could say. There are a few exceptions. Basically, water pumps designed for water below -10 and above 120 degrees Celsius fluid. Also, firefighting water pumps are outside the scope. Displacement water pumps are outside the scope, and self-priming water pumps as well, outside the scope. And when we look at the actual water pumps, there are 5 types which are recognized inside the regulation. 3 of these are what we call end suction pumps, and the more detailed limit of the end suction pumps is that they have to be designed for pressure less than 16 bars. The specific speed of the pumps has to be between 6 and 80 RPM. I'll cut back to that. The rate of flow has to be above 6 cubic meters per hour, so the smaller ones are excluded. And the maximum shaft power is 150 kW, so the very large ones are also excluded. And for the 4-pole machines, we have a maximum of 90 meters of head, and for the 2-pole machines, we have 140 meters of head as a maximum. So that limits, of course, the scopes a little bit. And all of these 3 are end suction pumps, but the one at the bottom is, of course, still an end suction pump, but it's placed in a vertical mode, so it's basically an inline pump in this case, but still it is an end suction pump. Then we have the vertical multistage pumps, which is up to 25 bars of design pressure. The number of stages is of course above 1, as it's a multistage pump. When we do the compliance testing, you have to take the model which has exactly 3 stages inside. And it also says in the text that if you are not able to have that, you must take the closest number of stages above 3 when you do the compliance testing. These are only valid for 2 pole machines in 2900 RPMs up to a rated flow of 100 cubic meters. And also you should note that this kind of pump is not only the inline versions. Sometimes you can see a top-bottom pump, which is still a vertical multistage, and this would be included as well. And the last type is, of course, the submersible multistage pumps. Again, more than 1 stage. In this case, we have to test the model with 9 stages. It's only for 4-inch pumps, the regulation, the 2-pole machines, and then again, the water should be designed for between 0 and 90 degrees Celsius. Yes, so that's the scope. And then we have the requirements inside the Ecodesign regulation. From January 1st, 2013, we need to have an efficiency on the pump in the best efficiency point, which could be calculated with a constant called C value at 0.1. I'll get back to that, but it basically means that we would exclude the 10% worst pumps on the market when applying this measure. Also, another duty point is the partial load point, again with the 10% worst, excluding them. And also we have a duty point in what we call overload, which again would exclude the 10% worst. On the first tier, we also had some product information requirements, a lot of them. I won't list them here, but we had, of course, you have to state the minimum efficiency index and year of manufacture and so forth. In the second tier, which was this year, 1st of January, we basically had the same 3 points, best efficiency point, partial load, and overload. But this time we increased the demand to 0.4, which basically means that we will exclude the 40% poorest water pumps from the scope. So, and this is effective now, of course, in European Union. If we look at this on a graph, in a schematic, we basically find what we call the house of efficiency, where we have the, let me see if this is working, we have the duty point here for best efficiency, we have the duty point here for overload efficiency requirement, and here we have the duty point for partial load. And if we put some rings on it, we can see this. These are the requirements. And if you look at the graph, you can see why it's called a house of efficiency. And when I do the compliance testing, I have to have all 3 duty points measured above these requirements. Of course, there's a tolerance, but it needs to be above in all 3 cases. The standards which is behind how to measure a pump in this case is, of course, the ISO 9906 from 2012, which I often refer to as the Bible of pump testing, as everything of importance in terms of testing a pump can be found there. How to measure differential pressure, how to calculate, how to measure electricity and so forth. So everything, all the measuring details can be found in this standard. And also we have, in the European level, we have very close to publishing, we have a standard called 16480. It's basically dedicated for the Ecodesign requirements, and it has inside cross-references to the actual regulation. But it's, I think right now it's in a voting stage on the European side, but I would expect it to be published this year next year in 2016 on the European level. But of course, I've been working also in the development of the standard and have been looking quite a lot in this during the testing in the past, of course. So, yes. So basically, when I want to test a pump, what we basically do when we have the specimen for compliance testing, the first thing we do, we put it in our testing facility, of course, and then we make the full pump curve from the pump. And I have an example here from my lab here. It's an anonymous pump. And you can see the full pump curve, which is blue, and all the crosses is actually the duty points that I made, and the line is a regression, mathematical regression between the points. In this case, we have a pump that can deliver water from 0 to 35 cubic meters and has a maximum head of a little above 40 meters. You will notice that I have quite a lot of duty points close to where I expect the best efficiency point to be. At this point in time, I'm not able to see exactly where this duty point is, the best efficiency duty point, but I can guess it. And when I do that, I take a lot of duty points close to my guess because I need those for later. So after measuring the complete pump curve, we dismantle the motor from the pump, and then we make a motor curve, but just a partial curve. In this case, I have measured from 800 to a little more than 3 kilowatts. But I actually make a curve from the input power efficiency as a function of input power, because that's basically the only thing that I'm able to measure when I measure the entire product, the motor and the pump connected. It's very rare, not to say it's quite unusual to be able to measure the shaft when handling a water pump. So we need to attack this problem from the outside, so to speak. So in the motor test facility, we test the motor isolated, and we have a curve. Again, the blue curve is basically the efficiency of this motor at different speeds. And now, when we have these numbers, we can go back to the full pump curve. And when we have the full pump curve and we know the corresponding efficiency of the motor in the pump, in the duty point, I can actually deduct the motor losses from the losses completely, and thereby isolating the water pump efficiency completely. And this is what I've done in this case. All the red crosses are the actual measuring points, the duty points. The green line is again the mathematical regression equation, which I can draw and I can calculate and I can even differentiate, so I can actually find the maximum of this curve. And in this case, the maximum was at 18.29 cubic meters per hour. And then it's quite easily to, from this, calculate or even just look at the head at this duty point, which in this case would be 31.74 meters. The flow for overload, which is 110% of the best efficiency point, would then be 20.11 cubic meters, and the partial load flow would be 13.71, and that this is at 75% flow. We also have the speed of the pump in this case. So all these numbers I can use to actually do the calculation. And from the regulation, I find this equation. And this equation is a little bit, well, I won't say complex, but you see you have x's and you have y's and x squared and y squared and so forth. And looking at the x, you can see this is the natural logarithm to the specific speed of this pump, and in this the flow and the head from best efficiency point is a part to calculate the specific speed. And also an important part of this equation is also the constant which we call C, because this constant is the one that was referred to in the regulation itself, as you saw earlier. And this basically refers to a scheme which looks like this in the regulation. This scheme comes directly from the European regulation. Here you can see the different kind of pumps, the different types of pumps from before, the same as before. And you can see the different variation in speed, 1450 and 1450 and 2900 speed here, for instance, between the end suction and own bearing pumps. And what you basically need for the requirement of Ecodesign, you need a constant. And if our example in this case is a vertical multistage pump at 2900, then at the first tier this constant would be 138.19, and in the second tier the same constant would be 133.95, and this basically means that from tier 1 to tier 2 on the same pump the requirement has now increased by 4.24 percent point. So that's an increase, of course, in the requirements for the pump. And equally on the partial load point and the overload point, it's just a fraction of the best efficiency requirement, and therefore it follows in the same manner. So going back to the actual calculation, this is part of the spreadsheet. First of all, we have the numbers from before, the 18, the 20, and the 13.7, and we have the head as well. And the pump type in this case is the vertical multiple stage with 3 stages. We can calculate the specific speed, which in this case is 35.7. We can calculate the constants X, Y, and Z, and then we can make the actual equation, which in the end gives us the requirement for this pump, inputting all the numbers. And in the end, I get a requirement of efficiency for this water pump to be 59.8. You will notice, of course, that the constant that I have used, the 138.19, comes from the first tier. It's actually down here as well, which is the 10% tier. And if I zoom this scheme a little bit, you can see that this case with this pump had a requirement of roughly 60% to the pump, and I measured it to 69, and the same goes for the partial load and the overload. So it passed all 3 duty points in this case, and the pump basically passed. So in conclusion, you have to measure the entire system, pump and motor. Then you have to isolate the motor efficiency to calculate the pump efficiency, and then you have to do the math and see if the pump passes, which it did in this case. Very good. Going to the circulators. We have the regulation on circulators, which was decided and published already in 2009, at the same time as the motor regulation as well. The input for the circulator regulation came also from the Lot 11 study in Europe, which finished in 2008. It started, the first tier was in January 1st, 2013, just like the water pumps, but the second tier on the circulators was not until August 1st in 2015, this year. So it's not too long ago the second tier was active, but now it is. And here you can see that the estimated energy savings from the circulator regulation is nothing less than 23 terawatt hours by 2020 compared to no measures. So the circulator regulation is it seems to have a lot more effect than the water pump regulation, but keep in mind that this was actually started, at least the intro to the circulator regulation was coming quite early, 2009. And another thing on the circulators, which is quite interesting, is that the circulator regulation is basically what we in other parts call an extended product approach, meaning that a circulator is in one small unit, both a motor control, a pump, and thereby we can define different duty points and load profiles. So in the end, the circulator regulation is about a weighted power consumption in 4 duty points where you take load profile into account. So in that sense, it's very different from the water pump regulation. Unfortunately, we saw in Europe quite a lot of aggressive partners in the circulator community trying to cheat the regulation. And it was so severe that we needed in Europe to have an amendment to the regulation, and this amendment was published in the summer of 2012, closing some loopholes. I don't think that they closed everything, but we did close quite a lot. And this regulation is called 622 from 2012. Yes. The scope of the circulators is glandless standalone circulators and glandless circulators integrated into products with a rated hydraulic power from 1 to 2500 watts. So that's basically all circulators for heating distribution, I think. A lot of it at least. What's not in scope is drinking water circulators. They have a requirement on product information, but not in terms of power consumption. And also, which is not in scope, what is not in scope is when you replace circulators with identical circulators on products which has been placed in the market before August 1st in 2015. Until January 1st, 2020, these circulators are excluded from the regulation. But after this, they are then included. The requirements is that the energy efficiency index in the first tier should be less than 0.27 or not more than 0.27, combined with a lot of product information, for instance, energy efficiency index, of course, and benchmarks and so forth. From August 1st this year, the same requirement was set down to 0.23, and also integrated circulators should meet the demands on the product information and so forth. So 0.23 is the requirement today in Europe, and the way we test this is basically in a proportional control mode on the circulators. You define 100-100 flow and head duty point, and then you draw a line down to half the head at 0 flow, and you make the 4 points at 25, 50, 75, and 100% of flow. And then you compare this weighted measured power consumption to a reference power. The reference power is basically calculated from the hydraulic power, which you find in the 100% duty point. I will show that later. And again, the standards for the circulators is, of course, the 9906, the ISO 9906 Bible for pump testing. This one is valid here, of course, as well. And then we have some dedicated standards in the European community called 16297 series. We have a part 1, 2, and 3, and they are basically dedicated standards for circulators in terms of Ecodesign testing, including cross-references and so forth. The part 1 is the general how to do it. The part 2 is to calculate on standalone circulators, and the part 3 is to calculate on integrated circulators. What we do in my lab is that we, again, make a full pump curve as the first thing. We warm up, of course, the unit overnight, more than 10 hours, it says in the in the standard, but we do it all night to avoid any run-in phenomena. In this case, we don't, or actually we cannot separate the motor efficiency because it's a circulator integrated. So we basically are able to calculate the hydraulic efficiency already at this point in time. Again, I have the crosses illustrating the duty points that I took. And again, we have a lot of duty points very close to the maximum hydraulic efficiency point. In this case, the maximum hydraulic efficiency was at 1.67 cubic meters per hour on this small circulator. In this duty point, we also had 2.43 meters of head. And when we know these two numbers, we can easily calculate the hydraulic power in this duty point, which is 11 watts in this case. And the 11 watts we then use to calculate the reference power, as I showed you before. And in this case, the reference power of this circulator would be 35.2 watts. So that's a number we're going to use later. The next thing we do is, and now I have zoomed the graph just a little bit, the blue line, sorry, this blue line here is the full pump curve here as before, and this cross here is the duty point that I just found, which is 1.67 and 2.43 meters of head. I go in and I draw a line on half the head, and then I put in the 4 expected duty points as it says in the standard. I also have, from each duty point, I have a 5% limit and I have a 10% limit in both directions. 5% is below and 10% is both above and below, because there are certain rules to which duty points you are allowed to use directly and which duty points you are allowed to use as linear regression and so forth. But in this case, these are the four duty points that I want to achieve in the test. This is what I actually tested. I programmed the circulator to do proportional, and then we did a lot of duty points, as you can see. The orange dot is actually illustrating, sorry, I need the mouse here. This orange dot and this one and this one and this one is illustrating the one duty point that I actually used. And these are the 4 duty points that I actually measured and are using in the calculation. What's important is the power consumption in the 4 duty points, which you see here. 30 watts, 20 watts, 23, 14, and 9. And if we proceed a little bit in the calculation, we have to weight these powers, and for that purpose we have a weighting scheme which has been used for many years in the European community. We often refer to it as the Blaue Engel weighting, but it basically is an average on which flows a standard circulator is operating in a standard heating system. So that basically means that the flow of 100% is only operated on average on 6% of the time. The 75% duty point is only 15% of the time. 50% flow is in 35% of the time, and 25% flow is in 44% of the time. So that's quite almost half of the time a circulator runs at 25% flow. Therefore, we have to weight these power consumptions. And that's what we do in this circle here. going down to 1, 3, 5, and 4 watts, we can multiply these. Sorry, we can add these, which gives 14.5, and then we have to divide it by the 35 from before, and we also have to multiply it by a factor called 0.49, which again gives me a number called 0.2023. So the final energy efficiency index on this circulator is 0.20, which means that it passes both the tier 1 and also the tier 2. So that's very good. What happens if a circulator does not pass the test? Then the manufacturer has to deliver 3 of the same circulators, and all 3 has to pass on average, and then the circulator will pass anyhow, and the first specimen is considered a statistical abnormality. Yeah. Okay. I will now try to go to the live thing, but first I will introduce or recap. If we look at the circulator, we have the 4 duty points looking like this, if you can recall that. Also recall the time in which the different flows are used, 6, 15, 35, and 44%. The example that I want to use today, you will be able to find on our webpage later on. Sorry, I just want to say that if we have an example of a circulator system where we have 6,000 hours per year running time, which is in the winter period, and it's closed in the summer period, then the spread of this flow would be something like 360, 900, 2160, 2,640 hours in this distribution of Blaue Engel. And then I have selected a circulator with 3 fixed speeds for the example. In this case, we use the pump curve for the maximum speed, which is called number 3, and the related power consumption we find down here, going down this way, and also the related efficiency of the system looks like this. And if I put in my duty points from the Blaue Engel, it would look something like this. We have a maximum flow of 38.0, which gives me 75% of 28.5. We have a half flow of 19 and a fourth flow of 9.5. And the corresponding heads we have up here, and the corresponding power consumptions we have down here. This would be my before situation. In my after situation, I would select a pump with proportional control and also ability to change the speed of the pump, which of course is necessary. In this case, we will have and achieve the same flows, 38, 28.5, 19, and 9.5. But in this case, we have less head, of course, because we do the proportional control, and the corresponding lesser power consumptions would apply, of course. So keep this in mind, and then I will try now to use the desktop if I succeed. Let me see.